All right, in this video, we're going to look at graphing a horizontal stretch or compression. So say you're given a problem like here's f of x, and you're going to find f of 1/2 of x. So a couple things I'm going to think to myself to start. First, I see that I'm multiplying. Multiplication lets me know that this is going to be a stretch or a compression. It's going to change the shape of the graph. If it was addition, then I would know that the shape stays the same. But this is going to change the shape because I'm multiplying. It's also happening to the input, so I know that it's going to happen horizontally. It can happen to the input changes it horizontally. It can happen to the output changes it vertically. So what I can do here that might be helpful is I can say to myself, what if I had a function, let's call it g of x, that was equal to f of 1/2 x. Okay, so how do I compare these two functions? Well, let's say I want to use this coordinate right here. What if I have f of -1? That would be g of what? Well, I can see here that I have replaced 1/2 x with -1. So 1/2 x is -1. If I divide both sides by 1/2 or multiply both sides by 2 to get rid of that, I can see that here x would have to be -2. So that's telling me g of -2 equals f of -1. G of a number equals f of half that number. G of a number equals f of half that number. So f of -1 is 3. G of -2 is also 3. So I can see the coordinate -2, 3 on my new function, f of 1/2 x. So this point goes to here, -2, 3. Let's take another key kind of point on the graph to keep going. So let's do this one right here. This is like 0, 2. So following in the same process as before, I'm going to say f of 0, which is 2. Okay, now I know that 1/2 of x is equal to 0. Well, since anything times 0 is 0, if 1/2 x equals 0, x must have been 0. So we know that g of 0 is also 2. So whenever you have a horizontal stretch or compression, the y-intercept actually stays the same. So that point will also be on our graph. So let's get another point here so we can kind of make sense of what's going on. This is the point 2, 0. So I'm saying that when I plug in 2 to the original function, what happens? So I plug in 2 here to the original function. That would give me out 0. F of 2 is 0. Okay, so again, f of 2, 2 is 1/2 is equal to 1/2 x. So I multiply both sides by 2, since 2 over 2 makes 1. I would get that 1x, or x is equal to 4. So again, when g of x is equal to f of half that number, so g of 4 is equal to f of half of 4. So g of 4 is what would give me 0 in this case. So that would be this number. So this point should not be here. This is on the black graph. But the new red point would be this guy right here. So this whole part here, as you can see, has been stretched horizontally. Let's do one more point, maybe to really take it home, and that would be this point 3, 1. Let's not make it red because it's actually on the original function. So we've got this point here, 3, 1. So f of 3 is 1. F of 3 is equal to g of 6. Because again, f of 1/2 of x is equal to g of x. So x must have been 6. So this is x, and this is 1/2 of x. Since f of 3 is 1, that means g of 6 is 1. As you can see, that point's going to be off what we can see right now, but we can tell that this graph is going to head off in this direction. So what's happening here is when b is 1/2, when b is less than 1, it actually causes a horizontal stretch. If you wanted a, that's not horizontal, that's how you spell it, but horizontal stretch. If you wanted a compression, you would actually pick a number that